Sound check. 1, 2, 3. Gravity assist. Gravity assist. So when we look out at night and we see the moon, it's spherical. But is it truly spherical? And how do we know how that moon is put together? Let's find out from an expert. Let's understand its gravity. Hi, I'm Jim Green, Chief Scientist at NASA, and this is Gravity Assist. This season is all about the moon. I'm here with Dr. Maria Zuber, the Vice President for Research at MIT. Welcome, Maria, to Gravity Assist.
Happy to be here, Jim.
Well, Maria, you've been involved in more than a dozen planetary missions, and one really special one because you were the principal investigator for the Gravity Recovery and Interior Laboratory, or GRAIL. That mission went to the moon. Can you tell me about the GRAIL mission and how it worked?
Well, the moon is an interesting place to measure gravity. It's the first planetary body other than Earth that we ever made a gravity measurement from. But it's very challenging to get a global map because the way we usually measure gravity is to look at the Doppler shift or the frequency shift of radio signal, because every spacecraft carries a radio. The Doppler shift is it's a frequency shift that happens when you're either coming towards something or away from something. So it's like a siren in an ambulance. When an ambulance is coming towards you, you go to higher frequencies, and when an ambulance is going away from you, it goes to lower frequencies. And all radio signals are just like that. You would actually be able to tell how fast the ambulance is going if you could actually measure the frequency of the siren. So in order to get a very good global map, we decided to send 2 spacecraft that measure the frequency shift or the Doppler shift of each other. And by doing that, we were able to get a spectacular gravity map of the moon.
Yeah, so as they orbit the moon, one gets pulled a little one way or another based on the gravity it's experiencing below it before the other one does, and that causes them to separate back and forth. Maria, when was GRAIL launched?
GRAIL launched in September of 2011. It took basically 3 months to get to the moon. Actually, the 2 spacecraft inserted into lunar orbit on New Year's Eve and New Year's Day, 2011, 2012. And it was to map for 3 months. And then just because of geometry of the way the 2 spacecrafts talk with each other, we needed to stop for 3 months and wait for the sun to come around so that we could get it on the solar panels while we were ranging, and then for another 3 months. And so, and then we did that one more time. So it went through 2012.
Well, you were the very first woman in planetary science who was a principal investigator, and I know that very well as head of planetary at the time. Maria, what does it mean to be a principal investigator?
Well, it's a lot of responsibility. So you have to be following all aspects of the mission.
You're essentially in charge of everything.
Yes, and I'll tell you, when the spacecraft was sitting on the rocket and it was ready to launch, I realized it was going to succeed or fail on the basis of decisions that I made, with a lot of help from my teammates and a lot of help from NASA. But ultimately, the principal investigator is
where the buck stops.
If things go well, everybody gets credit, and if things go wrong, the principal investigator gets blamed. The launch was where it really hit home about how risky this was, and it was like a dream because the team practiced launches many, many times and went through the whole sequence from the launching, and then the spacecraft, both spacecraft, they had to detach from the launch vehicle, and both of them had to work and with their solar panels and whenever we practiced, something always went wrong. I mean, something was always planned to go wrong so that we would practice figuring out how to deal with it. But when the launch actually happened, everything went perfectly, and none of us knew quite what to do. We just sat there. But the
and let it do its thing.
But the mission actually operated pretty flawlessly. Although I will say, later in the mission, when we brought the altitude down very low, I said it was like having a newborn baby that was up all night. That you had to just watch it constantly to make sure that nothing happened that we didn't know about, because you would have to do a close to immediate maneuver to avoid having one of the spacecraft crash into the surface.
So why do we care about the gravity in such great detail of the moon?
So if we look at the moon, these dark areas, the mare, there have been lava flows that have extruded on the surface, and you see very, very little of this on the far side. So the near side of the moon and the far side of the moon are extremely different. And, at the time that we were proposing GRAIL, the countries of Earth collectively had sent over 100 missions to the moon. And we still didn't know why the front side of the moon looked different than the back side of the moon. And so that told us that maybe the answer isn't on the surface. Maybe the answer is somewhere that we haven't looked before. And so we decided to look inside the moon.
And that's the gravity.
And that's what we measure gravity for, is to see, essentially map the inside of the moon.
So are there regions on the moon where the mass is larger than the surrounding areas?
If a planet was a billiard ball, if it was just completely uniform, and if it was completely round and spherical, then we would have a very, very simple gravity field. But planets are complicated. Planets formed by the accumulation of dust and gas from the solar nebula, and this material came together, and it coagulated into asteroids of different sizes, then, came together and then melted, and we had volcanic eruptions and comets hitting, and liberating water. So there's just all kinds of stuff going on planets, and this causes the gravity field to be what I call lumpy. That's what our students would call it.
So even
lumpy.
though it looks spherical, there are huge mass variations.
That's correct. And the type example of mass variations on the moon was recognized from the first satellites that we sent to the moon to do reconnaissance for where we should land astronauts. When the satellites were over the dark areas of the moon, these are the Maria, the spacecraft would get accelerated inward towards the moon. So they would deflect inward. It was because there was more mass in those areas that were tugging on the satellites and having them come a little bit closer to the moon. These anomalies were called mass cons, for mass concentrations, and one of the goals of the GRAIL mission was to determine what these mass concentrations were due to. That it turns out they're due to a combination of lava that filled crater basins. So the large circular areas that are dark on the near side of the moon are all impact basins, and when a large impactor hits a planetary surface, it excavates the crust and throws it away to some other place, and the mantle comes in and fills in underneath the crater. And this mantle tends to be more dense than the crust.
As you say, we really needed to figure out what the mass distribution of the moon was for humans to be able to explore. In fact, my understanding is when Neil Armstrong landed Apollo 11, and we're in the 50th anniversary for that, he landed it downstream from where they thought they were going to be because they didn't understand the gravity. And in fact, it took Collins to find them first. So it's too bad they didn't have GRAIL data before they did the Apollo program.
Well, it's a good thing we had Neil Armstrong at the controls for Apollo 11. But now any person, any robot who wants to land on the moon now, not knowing the gravity field will not be a problem. So we can now navigate very precisely. In fact, we know the gravity field of the moon now considerably better than we know the gravity field of the Earth.
Well, what do you think was the most surprising result from the GRAIL mission?
We knew that the crust of the moon would be broken up because when an impact hits a planetary surface, it breaks up the crust.
Shatters it pretty good.
I think none of us in the scientific community had any comprehension that the lunar crust was as shattered as it is. So the way that we were able to tell that was it turns out at short wavelengths that are consistent with the shallowest crust. 98% of the gravity is gravity due to topography, and only 2% of the gravity that we see is gravity due to anomalies or mass concentrations within the crust. And this is outside the Maria. And the only reason that could be the case is if the crust has been completely broken up and homogenized, because we talked earlier about all these processes going on that make planets lumpy and uneven. So the impact process has just evened everything out. But that 2% of the gravity within the crust is very, very interesting. For example, we found massive volcanic dikes that point to an earlier time on the moon when the moon heated up and expanded, and it had been hypothesized decades ago, and no evidence for it was ever seen at the surface. So it turned out that these dikes at the surface were all broken up by the impacts, but the dikes still exist very deep in the crust. So
the dikes are those things that squirt out lava.
That's right.
And form a wall.
The rocks melt deep and form the lava, and it rises up, and essentially like a crack, it fills up the crack, and that material is more dense than the crust. So it is a mass concentration, and we see it. But they're massive, but they're really intruding upon a crust that has been all broken up and homogenized. When you only see one side of the moon, that's something called synchronous rotation, and it turns out that synchronous rotation is a minimum energy state in a planet-moon system. So people are lazy, and it turns out planetary systems are lazy also. They want to do the least amount of work they could. So a planet with a moon will want to get to this synchronous configuration, and the moon got to this configuration pretty quickly. The question is, did this have something to do with why the lava flows are on the near side? If more of the mass is there, then it could be that that was the favored place for this minimum energy configuration to be worked out.
Well, one of the really unique imaging instruments you had on GRAIL was called MoonCam. What was the purpose of that instrument?
So MoonCam, the sole purpose of that experiment was educational outreach. Our outreach leader for the mission was Sally Ride. Sally was the first American woman to fly in space. She had a vision that we could put cameras on the GRAIL spacecraft, and that students in classrooms across America and actually internationally could download the software, learn how to use the software, and take their own images of the moon. And the challenge with that is that when you put an instrument on a spacecraft, this instrument, wasn't required for the science part of the mission. Therefore, it couldn't undergo as much testing and scrutiny and use the same kind of high-level parts for cost reasons. So it was a challenge to make it work. But I'll tell you, everybody on our team, most of the people had kids and grandkids, and everybody treated the cameras associated with MoonCam just like they did the radio systems on the spacecraft. So everybody thought it was important. So we had MoonCam took over 200,000 images of the moon, and Sally and I, we went out to classrooms across America, and we sat down in classrooms. I mean, there was a fear: is it only going to be affluent, classrooms on either coast of the United States? Classrooms in every state adopted MoonCam, and
Wonderful.
we went to some of these classrooms, and every kid in the class knew how to run the software. There was always one child or two who taught everybody else how to do it. And some students would say, "Well, I want to take a picture of a crater, or I want to take a picture of a lava flow." But then some students would say, "Oh, I would like to take a picture of wherever the camera is when it's my birthday."
Okay, sure.
And so the concept of MoonCam was that there are many images of the moon, but there's nothing like your image of the moon.
Correct.
So if you take your own image of the moon, it becomes deeply meaningful to you. And kids are smart. They will learn whatever they need to learn to do something interesting. And so Sally Ride Science, the nonprofit that led that experiment, they're actually tracking the MoonCam students now to find out what these students do in their careers. And
they had to know the moon really well to pick out what they wanted too.
We're going to have a lot of budding scientists. I think and hope.
Well, the moon is so important to the Earth. What are some of the reasons why we are so lucky to have a moon?
Well, other than the fact that it's beautiful and it gives us something that we can observe at night and something that we can aspire to study. And we have a big moon compared to other planets that have moons, because ours formed by a giant impact into the Earth, we believe. It stabilizes our climate because the tilt of the Earth is limited because of the force of the moon there. It's hard to overcome the force of the moon being nearby. And so, for example, the tilt of the Earth causes our seasons. The tilt of the Earth changes over time, but over many, many thousands of years on the Earth, it changes less than a degree. Okay, whereas if we didn't have a moon, the tilt of the Earth could change faster, and even though our tilt changes only very slightly, it's still enough to give us ice ages. So imagine if the tilt changed much quicker. So interestingly, Mars right now has a tilt almost the same as the Earth's. It's just coincidence because both the Earth's tilt and Mars's tilt change. But Mars's moons are tiny, so they don't have that stabilizing influence that Earth's moon does. So Mars goes through variations in its tilt, chaotic cycles, where there are times when the current poles of Mars get more heating from the sun than the equator does. And so that obviously has serious climatic consequences. And so there have been papers written where people have proposed that the presence of the moon actually helped facilitate life to develop. We don't know that life wouldn't have developed
if
the Earth doesn't have a moon. But for whatever beings or microbes, they would have had to be more adaptable in terms of their ability to handle different climatic conditions. If the Earth did not have a moon of the size it does.
Thinking of Mars now, do you think it'd be important to do a GRAIL-like mission at Mars?
Yeah, we've been thinking about that. GRAIL was based on a mission concept called GRACE, which mapped the Earth, and on the Earth, the two spacecraft couldn't get down real low because of the atmosphere, so you couldn't get the very, very super high resolution that we got for the moon. But when GRACE mapped the Earth, it measured changes in gravity. Changes in gravity due to water outflow and aquifers and ice sheets melting. And so there are actually really interesting changes that go on Mars, and Mars is a dynamic planet. So, for example, every year, and one Mars year is 687 Earth days, on every year on Mars, a third of its atmosphere exchanges with the polar caps. So it snows out on the polar caps. And this causes the gravity field of the moon to change by a part in a billion. And that's actually pretty big. I mean, it sounds like a small number, but a part in a billion we could measure with a GRAIL-like mission. So you could track the seasonal changes, and if there are underground aquifers on Mars in the present day, you would, if there are any changes in those aquifers, if, for example, in the summer season, if water thawed and flowed underground, it would be conceivably possible to track that.
Well, our next step in lunar exploration is the Artemis program, where we're going to have the first woman and the next man step foot on the south pole of the moon in 2024. So, Maria, how excited are you about that?
Send me.
Well, I can assure you the GRAIL data will be extremely important for that to happen.
I'm delighted to contribute in any small way that I can.
Well, Maria, I always like to ask my guests to tell me what was that activity, that person, place, or thing in their life that really got them so excited about planetary science that they changed their direction and it was accelerated to be the scientists they are today. And I call that a gravity assist. So, Maria, what was your gravity assist?
So actually, I'm an unusual case because I have wanted to study space since I was a baby in my playpen watching the first Mercury rockets. So that could be it, deciding to study space. But deciding to study planetary, when I applied to graduate school, I applied to both astrophysics programs and planetary science programs. And it was around the time that Voyager was flying past Jupiter. And I just said, when you go someplace and you look at something that you've never seen before, or you look at it at higher resolution or with a different set of eyes, discovery is assured. So it was really seeing, those images come back from Voyager that I think really drew me towards planetary science as opposed to the rest of the universe.
Well, that's great. Well, thanks so much for joining me on Gravity Assist.
Well, thanks, Jim. I'm happy to be here. And actually, let me just say that I love the title of this show.
Great. I do too. Well, join me next time as we continue our exploration of the moon. I'm Jim Green, and this is your Gravity Assist.